a quiet archive record. Tonight, we drift into the space beneath thought, where words slow down and silence begins to speak. The loudest sounds in the universe are not just a list of big bangs and broken records. They are events that move matter so violently that pressure becomes a weapon, a signature, and sometimes a clue. On Earth, sound is a pressure wave in air. In space, the vacuum does not carry sound the way air does, so the universe seems silent. But the universe is full of gas, plasma, dust, rock, and oceans. When energy hits those materials, it makes waves, shocks, and quakes. Instruments can translate those motions into audio, and when those motions happen at cosmic scale, the implied loudness can climb past anything made by humans. Tonight, we go through the loudest sounds in the universe. To talk about loudness in space, we have to start with a simple fact that feels like a trick. Sound needs a medium. In a perfect vacuum, there is nothing to squeeze and release, nothing to pass a pressure ripple along. That is why a movie scene of an explosion in space comes with sound. But real astronauts would see the flash and feel nothing in their ears. Still, most places in the universe are not a perfect vacuum. Space is thin, but not empty. Between stars there is gas, often only a few atoms per cubic centimeter, but that is still matter. In galaxy clusters, the space between galaxies is filled with hot plasma that can be denser than the average interstellar void. Inside planets, inside moons, inside stars, and inside the thick atmospheres of giant worlds, sound travels as pressure waves, just like it does here. There is another trick hiding in the word loud. Loud is a human feeling linked to our ears. Physics uses pressure, amplitude, and energy. A jet engine is loud to you because it pushes big pressure swings into the air, right where you stand, at frequencies your ear hears well. If the same engine ran in a very thin gas, the same mechanical power would produce far smaller pressure swings. The event might still be energetic, but it would not be loud to a nearby ear, because there is not enough medium to push against. So when people say the universe has sounds louder than anything on Earth, they are often doing one of three things. They are talking about a sound inside a dense medium, like an atmosphere or an ocean, or they are translating a pressure wave in gas or plasma into an audio signal for a speaker, then scaling it. Or they are using loud as shorthand for raw energy release and shock strength. A useful tool here is the decibel, which is a ratio scale. 10 decibels is 10 times more intensity. 20 decibels is 100 times. 100 decibels is huge in daily life. 120 decibels can hurt. A rocket launch close up can be over 180 decibels. But decibels always depend on a reference. In air at sea level, we can define a standard reference pressure. In the thin plasma between galaxies, that reference does not make sense. That is why many cosmic loudness claims come with a footnote. They are not saying your ear would be blasted at that level in the place the event happens. They are saying the pressure wave, if you could put it into air at Earth pressure, would be equivalent to that many decibels. Even with those caveats, it is still possible to build a real documentary sense of what qualifies as the loudest. We look for events that push strong shocks through a medium and keep doing it. We look for pressure waves that stay coherent over huge distances. We look for explosions that turn a large region of gas into a moving wall. and we look for situations where the medium is dense enough that the pressure change is meaningful. Let us anchor ourselves with a few Earth comparisons. Thunder is loud because lightning heats a channel of air to extreme temperature in a fraction of a second. The air expands violently, making a shock wave. At close range, a lightning strike can hit around 120 to 130 decibels. A nearby firecracker might be similar. A jet engine at takeoff might be 140 decibels near the source. A rocket launch can reach levels that are hard to even measure close up because the sound can damage sensors. That is the human scale. Now take the same idea of sudden heating and expansion and apply it to a star. A star flare can dump huge energy into a star atmosphere. The star atmosphere is plasma, a charged gas. It can carry waves. When magnetic fields snap and reconnect, they can launch pressure waves through the plasma. A solar flare on our sun is already a violent event on a planetary scale. But the sun is a relatively quiet star in the big zoo. There are stars called flare stars that erupt with much more extreme flares relative to their size. Still, if we want to chase the loudest, we need to look beyond stellar storms into the biggest structures that can ring like bells. One of the most famous cosmic sound stories comes from a place that is not exactly empty. It comes from a galaxy cluster, a huge swarm of galaxies bound together by gravity. In a cluster, most of the ordinary matter is not in stars. It is in the intracluster medium, a vast volume of extremely hot plasma. Hot means the particles move fast. But hot does not automatically mean dense. The intracluster medium is thin compared to air, but on the scale of a cluster, there is a lot of it. Near the center of some clusters sits a giant galaxy with a supermassive black hole. When that black hole feeds, it can launch jets. Those jets shove into the surrounding plasma and inflate bubbles, like a blowtorch underwater making cavities. When the bubble expands, it drives pressure waves into the plasma. In one famous case, astronomers found ripples in the X-ray glow of the cluster gas. Those ripples are pressure waves, basically sound waves, traveling through the plasma. If you turn those ripples into audio, the pitch is far below human hearing. The wave period can be millions of years, but if you scale it up, you can play it as a note. The key point is not the pitch. The key point is the power and the distance. The wave traveled across a medium that spans hundreds of thousands of light years. People describe that cluster sound as incredibly loud, sometimes with numbers like 230 decibels. The number is an Earth-air equivalent. It is meant to say the pressure wave, in its own medium, carries huge energy. Imagine a bell the size of a galaxy cluster, rung not once, but again and again by a black hole engine. Here is an analogy. Think about how sound spreads in a room. A shout pushes a wave into the air and it expands outward. The wave front grows, so the energy is spread over more area and the intensity drops. Now imagine you could shout in a room the size of a continent, and your voice remained coherent as it traveled. It would mean you injected extraordinary power. Now push that to the size of a cluster. That is what those black hole-driven waves represent. The intracluster medium also changes what sound means. In air, a strong blast wave quickly becomes a shock and then dissipates. In thin plasma, viscosity and conduction behave differently. The wave can travel far with less loss in some circumstances. It is not that it stays loud to a nearby ear. It is that the wave energy remains organized. If we are ranking cosmic loudness by sustained pressure wave power in a large medium, these black hole-driven ripples are near the top. The engine is not a single explosion. It is a long-lived system that can pump energy into its surroundings for millions of years. But the universe is full of one-time blasts too, and some of those are the sharpest punches nature throws. A supernova is the first obvious candidate. When a massive star dies, its core collapses, and the outer layers are blasted outward. A shock wave tears through the star. If the star has an atmosphere and surrounding gas, the shock slams into it. In the star itself, the medium is extremely dense. The pressure changes are extreme. If you could stand inside that star, the concept of loud would be meaningless, because you would be crushed and vaporized. But the physics is still a pressure wave, just in plasma and dense gas. Supernova remnants show us the afterimage of that shock. We see expanding shells, moving at thousands of kilometers per second. The shock compresses gas, heats it, and can accelerate particles. In a sense, the loudness of a supernova is measured by the strength of its shock and the amount of mass it can move. A supernova also has a hidden sound channel, not in air, but in neutrinos. Neutrinos carry energy out from the core in a burst. They barely interact with matter, so they escape. That is not sound, but it is a signal that arrives like a pulse. If we want actual sound waves that could be carried in a medium and in principle be heard, we can look at planets and moons. Because they have atmospheres, oceans, and solid crusts, that gives sound a place to exist in the usual way. Take Jupiter. Jupiter has a thick atmosphere and fierce storms. Lightning on Jupiter can be far more energetic than lightning on Earth. The air is different, made mostly of hydrogen and helium, and the pressure profile is different. A lightning discharge in that atmosphere can create thunder, like on Earth. But the scale of the storms and the energy can be larger. If you imagine standing on a floating platform in Jupiter atmosphere at a survivable pressure level, the thunder could be deafening. Now take Saturn moon Titan. Titan has a thick nitrogen atmosphere and liquid hydrocarbon lakes. Sound would travel differently there because the temperature is cold and the air is dense. A thunder-like event, if it happens, would carry far. In a dense, cold atmosphere, a sound wave can travel with less loss. A smaller source could be heard at longer distance, but the loudest planetary sounds likely come from impacts. An impact is a simple machine for making sound. A fast object hits a surface. Its kinetic energy turns into heat, fracturing, and shock waves in the ground and air. On Earth, the Chicxulub impact that helped end the age of dinosaurs would have produced a shock wave that circled the planet. It would have created a roar that was not a few seconds long. It would have been a global event. The atmosphere would have been slammed by a pressure front. The oceans would have been hit by massive waves and by acoustic energy in water. Now imagine a similar impact on a world with a thicker atmosphere or a global ocean. The sound in the ocean could be even more intense. Water carries sound very well. Whale calls travel long distances in Earth oceans. A large impact into water would drive shock waves that can travel through the ocean basin. If we widen to the solar system, the early period of heavy bombardment featured many large impacts. Each one would have been an enormous sound event inside planetary crusts and atmospheres. But the user asked for the loudest sounds in space and the universe. so we should be careful not to drift into only planet stories. Planets are great for intuition, but the true extreme is in compact objects and in the engines around black holes. Let us talk about compact objects. A neutron star is the remnant core of a massive star, packed so tightly that a teaspoon of its material would weigh about 1 billion tons. The crust is solid, but under immense stress. Magnetic fields can be trillions of times stronger than Earth field. Some neutron stars are magnetars, with fields so strong they can crack the crust. When a magnetar crust cracks, it is called a starquake. The star surface can shift by centimeters or meters, but the forces involved are enormous. The quake can cause the magnetic field to rearrange and release a burst of energy as gamma rays and X-rays. Around the star, the magnetosphere is plasma. Those changes can drive waves in that plasma. Again, the vacuum does not carry sound, but the plasma does carry waves. There can be oscillations that in some models ring like a bell, with frequencies that can be translated into audio. Some magnetar flares are among the most intense bursts of high-energy radiation seen in our galaxy. If one happened nearby, it could affect Earth atmosphere. The loudness here is not an ear sound, but the violence of the sudden change and the waves it launches in a medium. Now take two neutron stars in a binary system. They orbit each other for millions or billions of years, slowly losing energy by emitting gravitational waves. Gravitational waves are not sound in air. They are ripples in space-time itself. But there is an analogy that is surprisingly close. Gravitational waves have frequency and amplitude. A binary system chirps as it spirals in, increasing in frequency until merger. When scientists translate that chirp into audio, you can literally hear the pitch rise, because the frequency is in the range that a speaker can play when scaled. The physical effect of a gravitational wave on matter is tiny by the time it reaches Earth, but near the source, it is powerful. The energy release in gravitational waves during a merger can briefly exceed the combined light output of all the stars in the observable universe. That sentence is true in terms of power, but it is not the same as loudness to an ear. Still, if we broaden loudness to mean a wave that carries energy and has an oscillatory character, a gravitational wave event is a kind of cosmic sound. If you want a comparison, think of two heavy objects in water, circling and spiraling together, sending ripples outward. The ripples are not in water here, they are in the geometry of space. But the idea of a wavefront spreading is similar. In that frame, neutron star mergers and black hole mergers create some of the loudest wave events in the universe. They are like a drum hit that shakes the fabric of space. Now we reach the most classic loud thing in space in popular imagination, the gamma ray burst. A gamma ray burst is a brief flash of gamma rays, lasting from fractions of a second to minutes, often linked to the collapse of a massive star or to a merger involving neutron stars. They are seen across the universe. The energy is focused into narrow jets. If the jet points at you, the burst looks incredibly bright. The medium inside the jet is plasma and radiation. Shocks form inside the jet as faster material catches slower material. Those shocks are pressure waves in a relativistic flow. They are not audible, but they are violent. When the jet plows into the surrounding gas, it drives an external shock that produces an afterglow in X-rays, optical, and radio. That external shock is a bit like the sonic boom of a bullet, but at cosmic scale. A bullet compresses air and forms a shock cone, A relativistic jet compresses interstellar gas and forms a shock front that can be light years across. If you want a concrete analogy, imagine a speedboat that is not just fast, but nearly the speed of light, crossing an ocean of thin mist. The bow wave would be a shock, and the wake would be the afterglow. Now scale the boat to the size of a solar system, and the ocean to the space between stars. Another loud candidate is a quasar. A quasar is an active supermassive black hole feeding at a high rate, glowing brightly as matter heats in an accretion disk. The disk can launch winds and jets. The jets can carry enormous power, again pushing into surrounding gas and making lobes and bubbles. Over time, the quasar can heat the gas of its host galaxy and even influence star formation. In terms of pressure waves and shocks driven into a medium, quasars are long-term loudness machines. Now we should not forget the loudest sound you can actually hear in a medium. If you were there with ears that could survive, might not be in outer space at all. It might be in an atmosphere during a giant storm or during a giant impact. But for the spirit of the topic, we want the biggest wave events tied to cosmic engines. Let us build a set of categories. First category is sustained low-frequency pressure waves in large plasma volumes. This is the galaxy cluster ripples case. The pitch is absurdly low. The wavelength is enormous. The power is huge. If you turn the cluster into a speaker cone, it would be a note that takes millions of years per cycle. Second category is explosive shocks in dense media. Supernovae inside stars, impacts in atmospheres and oceans, volcanic events on large moons. These are giant shock factories. Third category is space-time waves, gravitational wave events. These have a clean sound-like character when translated and are literally measured as waveforms. To keep the story grounded, we can walk through a tour, starting with sounds you can picture in a familiar way and moving outward to the abstract. Imagine standing near a rocket launch. You feel the sound in your chest. It is not just a noise in your ears. It is a physical pushing and pulling on your body. That happens because the pressure swings are large and the air is dense. Now imagine the same rocket on Mars. Mars air is thin. The rocket engine is the same. But the sound would be much quieter because there is less air to transmit pressure. The rocket would still be violent, but it would not fill the landscape with the same roar. Now imagine a rocket launch on Venus. Venus has a thick atmosphere. Sound would be stronger there. A rocket would produce a huge roar and it might travel farther. The same power would push against denser gas. This is why we have to be careful when we say the loudest. The medium matters. The observer matters. But cosmic events often involve their own medium, like a star envelope, a disk, or a cluster plasma. In those places, the medium is what the event is acting on. Let us take a supernova and put ourselves in the outer layers of the star just before it explodes. The star is huge. Its outer layers are gas. When the core collapses, a shock wave starts in the deep interior and moves outward. When the shock reaches the outer layers, it can break out and flash. In the gas, that shock is a pressure front moving faster than the local sound speed. It is literally a supersonic wave. The pressure jump can be enormous. It can accelerate gas to thousands of kilometers per second. The sound speed in a hot stellar atmosphere can be tens to hundreds of kilometers per second, much higher than in Earth air, but the shock is faster still. So if we think of loudness as shock strength relative to the medium, this is an extreme. Now step away from the star and look at the circumstellar environment, the gas the star has shed. When the supernova ejector hits that gas, it makes another shock, like a giant plow. That shock can light up in radio and X-rays. If you had a microphone in that plasma, it would pick up the passing pressure wave. Now let us step to an even bigger engine, a black hole jet in a cluster. The jet is narrow, but it carries power for millions of years. It punches into the plasma and inflates cavities. The cavities are surrounded by bright rims of compressed gas. Those rims are the equivalent of a loudspeaker cone pushing outward. Each expansion drives a wave. If you want to picture the scale, take the sun and shrink it to a grain of sand. The galaxy would still be huge. Now take a cluster and imagine it includes hundreds or thousands of galaxies. The plasma between them is the medium. The black hole at the center is a motor. The motor is small compared to the cluster, yet it can shake the whole medium. In terms of human hearing, the note is too low. But loudness is not just pitch. It is pressure, amplitude, and power. The black hole can keep feeding energy into the medium over and over. Now let us talk about another kind of cosmic noise that is closer to our ears, radio noise. Radio waves are electromagnetic, not sound. But radio telescopes can convert radio intensity patterns into audio. Pulsars, for example, are spinning neutron stars that beam radio pulses. If you turn that into sound, you get a ticking or a buzzing. The loudness in that audio is not physical pressure. It is the strength of the radio signal. Fast radio bursts are another case. They are brief flashes of radio waves, lasting milliseconds from far away. They can be so bright in radio that for a moment they can outshine everything else in that part of the sky at that frequency. The physical source might be magnetars or something else. The implied energy is huge. Again, not sound. But it is an event you can render as an audio pop. There is also the idea of the cosmic microwave background, the hiss that is left from the early universe. That hiss is not a sound in air, but it can be translated. But the request is about loudest sounds, so we should not turn this into a tour of translated signals. The best story is about pressure waves and shocks, so here is a bold claim to test. The loudest sound in the universe might be the shock wave of a massive black hole outburst traveling through a galaxy cluster plasma. That is because it can involve an enormous mass of medium and a long duration. There is evidence for massive outbursts where cavities in cluster gas require tremendous energy to inflate. The ripples seen in X-rays are interpreted as sound waves that can dissipate energy and heat the gas. This is a key idea in cluster physics, because without heating, the gas would cool and flow inward too fast. The black hole feedback solves that. Now consider what it means to have a sound wave that heats a galaxy cluster. On Earth, sound waves carry energy, but the heating is small unless the wave is strong or the medium is special. In a cluster, these waves can be part of the energy balance. The wave is a heat transport mechanism. If you want an analogy, imagine a giant bath of thick soup that wants to cool and settle. In the center is a motor that periodically punches bubbles into it. Each bubble sends ripples. The ripples spread and stir and keep the soup warm. That is black hole feedback. The word loud fits because ripples are sound like waves. The scale fits because the medium is enormous. Now, loudness can also be sharp. A single detonation can have a higher peak. So we should compare sustained power to peak power. A supernova has a huge peak, but it is brief. The shock is strongest early. The wave moves out and expands. A gamma-ray burst jet might have an even higher peak power, but the medium it acts on is thinner. A merger of black holes can have a giant peak in gravitational wave power. So we can ask, what is the loudest by peak wave power of any kind? For gravitational waves, there are events where tens of solar masses worth of energy are radiated as gravitational waves in a fraction of a second. That is an extreme power in the same units as watts. It dwarfs the light output of entire galaxies during that moment. If you treat that as sound in space-time, it is hard to beat, but you cannot hear it as pressure. The wave stretches and squeezes space, and the effect on matter is tiny unless you are very close. If you were near the merger, the tidal forces and radiation would destroy you. So the idea of hearing is hypothetical. Still, for a documentary story, it is fair to say that the universe has a class of sounds that are not in air, but in space-time, and those are among the loudest wave events. Now let us go back to pressure waves that could in principle hit an ear inside a medium. The densest natural medium in space, outside of stars, includes things like planetary atmospheres, planetary crusts, and oceans. Gas giants have thick atmospheres. Some moons might have subsurface oceans. Inside those, a shock can be loud. Think about the great red spot on Jupiter. It is a storm larger than Earth. The winds are fierce. If lightning is present, the thunder could be immense. But we do not have a direct microphone there. On Saturn, lightning storms have been detected and called Saturn electrostatic discharges. They are powerful radio bursts and imply large lightning. The thunder in a thick hydrogen-helium atmosphere could be deep and booming. Now imagine the sound of a meteor entering such an atmosphere at high speed. On Earth, a bolide can create a sonic boom that can shatter windows. On a denser atmosphere, the boom could be more powerful. But the most dramatic sound would be an impact that excavates a crater. The shock would travel through the ground as seismic waves. Seismic waves are again not sound in air, but are elastic waves in rock. They can be translated into audio too. They can be large. In fact, if we widen the definition again, earthquakes are sounds of a planet. The planet rings. After a big quake, Earth has normal modes, vibrations that last for days. Those are very low frequency, like a bell. The same is true for other worlds. A huge impact on a moon could set it ringing. So the loudest sound in the solar system in a rock medium might be a giant impact, because it injects huge energy into the crust and mantle. Now expand beyond. There are exoplanets with thick atmospheres and violent weather. There may be worlds with global oceans under thick ice. In those oceans, a large event could make huge acoustic waves, but we cannot measure these directly today. So for evidence-based documentary, we stick to the things we can observe. We can observe supernova remnants. We can observe cluster ripples. We can observe radio and X-ray shocks. We can observe gravitational waves. So let us walk through a sequence of scenes. First scene is a lightning strike on Earth. The channel heats, the air expands, the shock wave forms, and you hear thunder. It is loud because the medium is dense and the temperature jump is sudden. Second scene is a volcanic explosion. A volcano can blast ash and gas into the air, making pressure waves. The loudness can be extreme near the vent. The event can produce infrasound, very low frequency sound waves that travel long distances. Third scene is a meteor airburst. A rock enters the atmosphere at tens of kilometers per second. the air in front compresses and heats. A shock wave forms. The body can fragment and explode, producing a blast wave. The Chelyabinsk event in 2013 produced a shock that broke windows many kilometers away. Now we jump to a supernova. It is like a meteor impact, but inside a star, and the mass involved is enormous. The shock is a global wave through the star. Now we jump to a cluster. The black hole outburst is like a motor punching bubbles into a huge bath of plasma. The pressure waves are like infrasound that travels across the cluster. Now we jump to a merger of neutron stars. The event emits gravitational waves that chirp. If you convert the chirp to audio, you hear a rising tone. Now we jump to a merger of black holes. The ringdown is like a struck bell in spacetime. The waveform settles into the final black hole. All of these are sounds in the broad sense of waves carrying energy. Now, to make comparisons, we can try to put numbers to these events. But we must be careful. Decibels are often used in press reports. For the cluster ripple case, numbers like 230 decibels are sometimes quoted. That number is beyond anything we experience. It is not a real ear experience. It is a translation. To understand why the number can be so high, recall that decibels are logarithmic. Each 10 decibels is 10 times intensity. So moving from 130 decibels thunder to 230 decibels is not just a bit louder. It is 10 billion times more intensity. That sounds absurd. But again, that is in a different medium. Another way is to compare energy. A supernova releases about 10 to the 44 joules of energy. That is a 10 with 44 zeros. Most of it is in neutrinos. The kinetic energy of the ejector is about 10 to the 44 joules. That is enough to unbind the outer layers of a star. A black hole outburst that inflates a huge cavity in cluster gas can require energies of similar scale or more. Over long times, the black hole can inject enormous energy. A neutron star merger can radiate a few percent of a solar mass in gravitational waves, which is about 10 to the 47 joules. That is huge. But again, different channel. So which is loudest? It depends on what you measure. If you measure peak power in gravitational waves, compact object mergers are top tier. If you measure sustained pressure wave heating of a medium, black hole feedback in clusters is top tier. If you measure peak shock strength in dense gas, supernova shocks are top tier. Now the beauty of this topic is that it lets us look at the universe not as a silent picture, but as a place full of motion that can be treated as sound if you know how. Scientists often use the word seismology for earthquakes and helioseismology for sunquakes. Helioseismology is the study of sound waves in the sun. The sun is full of acoustic waves. Convection in the outer layers generates waves that bounce around inside. By measuring tiny motions on the surface, scientists can infer the sun interior. The sun rings with many modes. It is like a huge musical instrument. If you speed it up, you could hear it. Other stars have similar oscillations. That is called asteroseismology. It is a way of hearing the interior of a star. These stellar sounds are not the loudest by raw energy, but they are beautiful in a documentary sense because they are real pressure waves in plasma. Now consider a star that undergoes a flare. The flare can excite waves. It can send shocks through the star atmosphere. Now consider a star that is in the process of dying. In the final phases, the core can pulsate. The envelope can have large oscillations, and then the collapse happens. So, in some sense, The universe is always humming, but at frequencies and scales far from human experience. Let us go deeper into one iconic case, the cluster ripple that got popular attention. In the center of a certain cluster, there is a galaxy with an active black hole. X-ray observations show the hot gas around it. In those images, you can see faint concentric ripples, like rings in a pond. Those are interpreted as pressure waves. Each ring corresponds to a wavefront moving outward. They likely come from repeated outbursts as the black hole jets inflate bubbles. The wavelength is enormous. The period is millions of years. The amplitude is small in relative terms because the gas is hot and the sound speed is high. But the energy carried can be large because the volume is huge. If you were a molecule in that plasma, you would feel a slight change in pressure and density as the wave passed, like a slow tide. But because the wave spans such a large region, the total energy is immense. This is a key lesson. Loudness can come from amplitude, but it can also come from scale. A small pressure change over a huge mass can still be a huge total energy transport. Now compare to a rocket launch. The pressure change is large, but the volume of air affected is small compared to a cluster. So the cluster wave can be described as louder in terms of energy in the wave. Another iconic case is a supernova in a dense circumstellar medium, sometimes called a Type 2in supernova. In these, the star has shed a lot of material before it explodes. When the ejector hits that dense shell, the shock is strong and radiates a lot. It is like an explosion inside a fog bank. The interaction can last longer and can be very bright. In terms of pressure waves, the shock in that dense shell is intense. It can accelerate gas and heat it. Now, if you could place a microphone in that shell, it would record a passage of a shock and then a turbulent roar as the region mixed. But again, it would be at frequencies and in a medium not like Earth air. Now consider a hypernova, a very energetic explosion, sometimes linked to long gamma-ray bursts. The energy can be larger than a typical supernova. The shocks can be stronger. Now consider the explosion of a star called a pair instability supernova, in which the star can be completely disrupted. This can happen for very massive stars. It is like a total demolition. These are rare, but they are among the most energetic stellar explosions. Now let us not forget the early universe. In the early universe, before atoms formed, the universe was a hot plasma. Photons were tightly coupled to matter. Pressure waves could travel in that plasma. These are called baryon acoustic oscillations. They are literally sound waves in the early universe. Those waves left an imprint that we can measure today in the distribution of galaxies. It is like a fossil sound. If you could be in the early universe, it would be a hot glowing sea with pressure waves traveling. The frequencies would be extremely low compared to human hearing, but the physics is sound. The loudness is hard to define, but the concept is deep. The universe had a sound stage. Now, there is a temptation to make everything into a sound. But the best way to respect the documentary style is to keep returning to the medium and the wave. So let us define sound in this story as any wave that moves matter back and forth in a medium, or any oscillatory wave that carries energy and can be mapped to frequency. With that definition, we can include plasma waves and gravitational waves, but we should always label them. Now, we can build a comparison ladder. At the bottom are everyday sounds in air, like speech, music, and traffic. Above that are natural loud sounds on Earth, like thunder and volcanic blasts. Above that are human-made extremes like rockets and explosions. Above that are planetary scale events like large impacts and global storms. Above that are stellar scale events like flares and supernova shocks. Above that are galactic and cluster scale pressure waves driven by black holes. And in a separate channel are gravitational wave events from compact mergers. Now, to keep the listener engaged, we can explore some vivid comparisons. One comparison is to imagine decibels as a staircase where each step is a tenfold increase. If thunder is around 120 decibels and a rocket can be 180, that is 6 steps, 1,000,000 times more intensity. Already huge. Now imagine a 230 decibel equivalent. That is 5 more steps, 100,000 times more than the rocket in intensity, but again in a different medium and different reference. Another comparison is to imagine the wavefront size. A thunder wave might be heard across a few kilometers. A supernova shock might span light years. A cluster wave spans hundreds of thousands of light years. Another comparison is time. Thunder lasts seconds. A supernova shock is strong for days to months in terms of breakout. Then the remnant expands for thousands of years. A cluster wave can take tens of millions of years to cross the core. Now, there is another kind of loud that is more personal, the suddenness. A crack of thunder is sudden. A gunshot is sudden. Sudden sounds can be startling. In space, a gamma ray burst is sudden in light, and a gravitational wave chirp is sudden in frequency rise. So loudness can also mean a rapid change. Now, let us do a case study of the loudest sound a person could actually hear if they could safely be present. Suppose you are on a platform in a thick atmosphere on an exoplanet, and a nearby object enters the atmosphere and detonates. The shock would slam the air. The sound could be beyond the range of your ear. It could cause damage. That is an ear-loud event. But in most cosmic cases, there is no ear. So the story becomes about how we infer and translate. Astronomers are like remote listeners. They do not place microphones in a cluster. They infer pressure waves from brightness changes, density changes, and temperature patterns. They infer shocks from spectral lines and from radio emission. They infer gravitational waves by measuring tiny length changes in detectors. Then they translate those measurements into audio for human intuition. This translation can be honest if we keep the mapping clear. Now, to keep the analogies strong, think about this. A sound wave in air is a pattern of compression and rarefaction. In a plasma, you can have similar compressions and rarefactions, but also waves tied to magnetic fields, like Alfvén waves. In space-time, a gravitational wave is a pattern of stretching and squeezing. In each case, something oscillates, and energy moves outward. Now, we can ask a question that feels simple but is not. What would the universe sound like if you could hear it? If you could hear pressure waves in gas and plasma, you would hear deep rumbles, slow pulses, and the roar of shocks. Most of it would be infrasound, far below your ear. You would need a kind of cosmic subwoofer. If you could hear the sun interior, you would hear a constant low murmur of modes. If you could hear a supernova shock, you would hear a rising roar as the shock passed, and then a long tail of turbulence. If you could hear a black hole outburst, you might hear a periodic deep pulse as bubbles formed and waves moved. And if you could hear gravitational waves, you would hear chirps and ringing. Now, Another strong comparison is to the idea of sonic booms. A sonic boom happens when an object moves faster than the local sound speed. The wavefronts pile up into a shock. On Earth, a supersonic jet makes a boom that can be heard for many kilometers. The shock carries a sharp pressure change. In astrophysics, shocks are everywhere. They form when flows are supersonic relative to the medium. In space, flows can be supersonic because the sound speed depends on temperature. In cold gas, sound speed is low, so many flows are supersonic. Supernova remnants are classic shock waves. The expanding shell is supersonic relative to the surrounding gas. The shock heats the gas and accelerates particles. Jets from young stars also make shocks as they plow into surrounding gas. Even the solar wind makes a shock at the boundary of the heliosphere. So the universe is full of booms. But the loudest booms are those with the most energy and the largest medium. Now let us consider a special case. There are galaxy cluster mergers. When clusters collide, the gas in them slams together. This can create enormous shocks in the intracluster medium. Some of these shocks are called bow shocks, like the shock in front of a supersonic plane. A famous example is the bullet cluster, where a subcluster plows through a larger cluster, creating a shock front seen in X-rays. The shock front is huge, hundreds of thousands of light years across. That shock is like a cosmic sonic boom. In terms of pressure waves, a cluster merger shock could be one of the loudest events in a medium, because it involves enormous mass and huge velocities. This is a great candidate for loudest, because it is a direct shock with a huge area. Now compare that to the black hole ripple. The black hole ripple is more like a sustained tone. The cluster merger shock is more like a single huge crack, which is louder. Again, depends on measure. Now, there is also the concept of the cosmic web, filaments of gas connecting galaxies. Gas flows along filaments and into clusters. Shocks can form at the edges of filaments and around clusters as gas falls in. So even the growth of structure in the universe involves shocks and pressure waves. In the early universe, sound waves set the scale of structures. Later, gravity and shocks shape them. So the loudest sounds are tied to the same processes that build the universe. Now, to give the listener more concrete scale, let us quantify a few things. The speed of sound in Earth air at room temperature is about 340 meters per second. In water, it is about 1,500 meters per second. In steel, it can be about 5,000 meters per second. In hot plasma, the sound speed can be hundreds of kilometers per second. In cluster gas, at tens of millions of degrees, the sound speed can be around 1,000 kilometers per second. So a shock moving at 2,000 kilometers per second in cluster gas is only Mach 2. It is supersonic, but not absurd. In supernova, ejecta, moving at 10,000 kilometers per second in cold interstellar gas where sound speed is a few kilometers per second, the Mach number can be thousands. That is a very strong shock. Strong shocks are loud in the sense that the pressure jump is huge. Now, in a dense medium, like a star envelope, the sound speed can be much higher, but the shock is still strong. Now, here is a comparison. A strong shock in air can be like the shock from an explosive. A strong shock in interstellar gas is like an explosion in a much thinner medium. But because the velocities are huge and the scales are huge, the total energy is enormous. Now let us do a short tour of specific loud sources. There are stellar winds from massive stars. These winds can collide and form shocks, producing X-rays. In a binary system of two massive stars, the winds collide and produce a shock region. That region is like a constant supersonic collision, a continuous loud factory. There are colliding galaxy clusters producing giant shocks. There are active galactic nuclei producing bubbles and sound waves. There are supernovae producing expanding shocks. There are magnetars producing starquakes and bursts. There are mergers producing gravitational wave chirps. And there are impacts and storms in planetary atmospheres. Now, the phrase loudest sounds in the universe can also invite a more playful comparison. Like, what is louder than a rocket? A rocket is loud because it pushes a lot of gas fast. Now imagine a star that throws off a wind that has the mass loss rate of a sun per year and a speed of thousands of kilometers per second. That wind would carry huge momentum. Now imagine a black hole jet that carries power equal to 1 trillion suns, focused into a narrow beam. That is a cosmic blowtorch. Now imagine two black holes colliding and converting mass into gravitational wave energy. That is a cosmic drum. Now imagine a cluster merger shock moving a wall of gas across hundreds of thousands of light years. That is a cosmic boom. These are the contenders. Now, to answer the question in a way that feels like a conclusion, we can say this. If you mean loudest in terms of pressure waves, in a medium on the largest scales, the strongest known candidates are the shocks and sound waves in hot cluster gas, driven by black holes and by cluster mergers. If you mean loudest in terms of wave power of any kind, the strongest known candidates are gravitational waves from compact object mergers. If you mean loudest that a human ear could in principle hear in a familiar medium, the strongest known candidates are giant impacts and massive explosions in dense atmospheres and oceans. Now, let us linger on a final set of analogies to make this feel real. Picture a pond. Drop a pebble, you get ripples. Drop a boulder, you get bigger ripples. Drop a truck, you get a splash and a shock wave. Now replace the pond with the hot gas in a cluster. Replace the pebble with a small black hole outburst. Replace the truck with a major outburst. The ripples are the cluster sound. Picture a bell. Strike it, it rings. Now imagine a bell made of space-time. Two black holes merge and the final black hole rings down. That is the gravitational wave ring down. It is like a note that fades. Picture a sonic boom. A jet crosses the sound barrier. Now imagine a galaxy cluster merger shock. The subcluster moves supersonically through hot gas. The shock is the boom. Picture thunder. Lightning heats a column of air. Now imagine magnetic reconnection on a star. It heats plasma and launches waves. The universe is full of these patterns. And the last twist is that, in many cases, the loudest events are not the brightest. A gravitational wave event can be the most powerful wave in its channel, yet almost invisible in light. A cluster ripple can be huge in energy, yet subtle in an image. A shock can be seen as a faint edge. That is why scientists often say we are entering an era of multi-messenger astronomy. We listen in more than one way. We have telescopes for light. We have detectors for gravitational waves. We have neutrino observatories. Each one is a way of hearing. So the loudest sounds in the universe are not only the things that would blow out your ears. They are the things that move the most matter, push the strongest waves, and leave the clearest ring in the fabric of reality. There is one more angle that makes the question feel real. sound is not only about how much energy exists, it is also about how that energy couples into a medium. An explosion in vacuum can be blinding, but it does not punch a pressure wave into nothing. The loudest cosmic events often happen in places with enough material to push. That is why galaxy cluster gas matters. That is why supernova shocks matter. That is why impacts matter. A good comparison is to think about two rooms. In one room, there is thick fog. In the other, there is almost no air. If you set off the same explosive, the blast in the fog will drive a stronger pressure front because there is more material to compress. The energy is the same, but the sound wave is different. In the thin room, the pressure wave is weak because there is less medium to carry it. This is also why some of the most dramatic shock signatures in astronomy happen when a fast flow hits a dense target. A supernova expanding into very thin gas makes a broad, smooth remnant. Supernova slamming into a dense shell makes a bright, sharp edge. It is like the difference between a hammer strike on a pillow and a hammer strike on a hard table. The second case produces a stronger wave because the material resists and pushes back. When astronomers talk about shock strength, they often use the Mach number, the speed of the flow divided by the local sound speed. A higher Mach number means a stronger shock. In cold interstellar gas, the sound speed can be only a few kilometers per second. A supernova shock moving at thousands of kilometers per second can be a Mach number of hundreds or more. That means the gas is slammed into a thin, compressed layer. The temperature behind the shock can jump by millions of degrees. Magnetic fields can be amplified. Particles can be accelerated to near light speed. If you could translate that into a human sound, it would not be a clean bang. It would be more like an endless tearing roar, because the shock front is not a point. It is a moving surface, the size of a solar system, and then the size of a light year, sweeping up new gas the whole time. Now think about the bow shock of a cluster merger. The medium is much hotter, so the sound speed is high. The Mach number might be only 2 or 3, but the area is vast. The shock can span hundreds of thousands of light years. Even a modest pressure jump across that front, applied over that area, represents a huge energy transfer. A way to picture this is to imagine a small but very sharp crack of a whip compared to the slow push of a bulldozer. The whip has a high peak. The bulldozer moves more total mass. In cosmic terms, a supernova can look like the whip. A cluster merger shock can look like the bulldozer. There is also a class of loud events that happen around forming stars. When a young star grows, it can launch jets. Those jets punch into the surrounding molecular cloud, which is cold and dense. The jet is supersonic, so it forms shocks. These are seen as Herbig-Haro objects. They are bright knots where the jet hits gas. On the scale of a star-forming region, these shocks are like constant bangs, repeated as the jet pulses. They are not the loudest, but they show that shock-driven sound-like behavior is common at every scale. Now consider the sun again, but not as a quiet yellow star. Consider a solar coronal mass ejection. A coronal mass ejection is a huge bubble of plasma launched into space. It can drive a shock in the solar wind. That shock can be detected by spacecraft. It is a kind of moving pressure wall. When it hits Earth's magnetosphere, it can trigger geomagnetic storms. If Earth had ears for plasma waves, it would hear that impact as a deep thump, followed by a long period of disturbed motion. This gives another comparison. The loudest cosmic sounds are often not single points. They are walls and shells. A shell moving through a medium is like a drum skin, but one that expands. Now, there is a final category that feels like sound, but is not. It is the background of gravitational waves. Just as the early universe left behind a microwave background, the universe may have a background of gravitational waves from many distant events. That would be a kind of cosmic hiss in space-time. It would not be a pressure wave in gas, but it would be an ever-present ripple. Scientists are searching for this background using pulsar timing arrays. Pulsars are precise clocks. If a gravitational wave passes between Earth and a pulsar, it slightly changes the travel time of pulses. By watching many pulsars, scientists can look for a shared pattern. If detected, it would be like hearing a low rumble made by countless supermassive black hole binaries across the universe. In that sense, the universe may have a permanent base node. So when we ask for the loudest sounds, we are really asking what events and systems push the biggest waves through the biggest media, or through space-time itself. On the scale of planets, the loudest would be giant impacts and enormous atmospheric blasts. On the scale of stars, the loudest would be supernova shocks, hypernovae, and violent eruptions that move huge mass at high speed. On the scale of galaxies and clusters, the loudest would be the great shocks of cluster mergers and the long, repeated pulses driven by feeding black holes. And in the separate channel of space-time waves, the loudest would be the mergers of compact objects, where the waveform carries a sharp, rising chirp and then a final ring. Each of these is a different kind of loud, but all of them share the same core idea. A wave takes energy and carries it outward, leaving a pattern that can be measured long after the source is gone. That is how we listen to a universe that has no air, but never stops moving. One more way to compare these extremes is to think about what a shock does to information. In ordinary sound, a loud noise can drown out a quiet one. In astrophysics, a strong shock can drown out the older history of a region. It compresses gas, it heats it, it erases fine structure, and it redraws the map. In a supernova remnant, the shock can sweep up the interstellar medium and pile it into a shell. Inside the shell, the gas is hot and turbulent. The remnant can light up in radio because electrons spiral in magnetic fields. That radio glow is a record of the shock, like a long exposure photograph of a bang. In a cluster merger, the shock can create a sharp edge in X-rays, a sudden jump in density and temperature. It can also accelerate particles and create radio relics, long arcs of radio emission that trace the shock front. These relics are like the foam line at the edge of a giant wave. So loudness in the universe is often visible. You cannot hear it directly, but you can see its consequences. A loud event is one that leaves a clear boundary, a clear ripple, a clear shell. And when we translate these measurements into sound for human ears, we are not adding drama. We are doing what scientists do with all data. We map it into a form our brains can compare. A light curve becomes a tone. A waveform becomes a chirp. A ripple becomes a note. The universe does not provide air for our ears, but it provides enough structure that we can still listen in our own way. If you want one image to keep, think of the biggest sounds as waves that never had an audience, only witnesses. Gas, plasma, rock, and space-time itself take the hit. Carry the ripple and keep the record. Across all these scales, the pattern repeats. A A strong source makes a shock. The shock becomes a wave. The wave spreads, fades, and still changes everything it touches. This was a quiet archive story. Where the story ends, sleep begins.